What derivatives tell us? Part 2. In part 1, we talked about how the second derivative being negative coincides with a function being concave down, and the second derivative being positive coincides with the function being concave up. If the second derivative is 0 and the second derivative changes sign, then you have an inflection point. I said in part 1 that we were going to follow these 4 steps using an example, and the example I'd like to use is a polynomial. First, let's find where the second derivative equals 0. I find the first derivative and the second derivative. I set the second derivative equal to 0 and I solve for x. To do that, I divide both sides by 12 and factor the left-hand side. And that gives me my possible inflection points. After I find my possible inflection points, I use the domain and those possible inflection points to find subintervals. Well, the domain of a polynomial is all real numbers. So I take the number line and I break it up using my possible inflection points. After I do that, I check each subinterval for the sign of f double prime. So is f double prime positive or negative on each subinterval? For the first subinterval, I use a test point of -1, and I find that my second derivative is positive, and that tells me my function is concave up. On my second subinterval, I use a test point of 0, and I find that my second derivative is negative, telling me my function is concave down. On my third subinterval, I use a test point of 2. I find that my second derivative is positive, telling me my function is concave up. After I find where my function is concave up and concave down, then I go to step 4 and I look for changes in concavity. And the 2 possible inflection points are, in fact, inflection points. So -1/3 is an inflection point because I go from concave up and concave down. And x equals 1 is an inflection point as well because I go from concave down to concave up. So my first interval, notice that I have concave up, and then concave down, and then concave up again. I'd like to switch gears slightly and talk about something called the second derivative test. The second derivative test is a way of determining if a critical point is a max or a min, and here's how it runs. If you want to use the second derivative test, you first find critical points of a function. Then, if at a critical point the second derivative is negative, then your function is concave down there. Concave down at that point, telling you that your critical point is a maximum. So a negative second derivative goes along with a local maximum. If the second derivative is positive at your critical point, then you have a local minimum. If your second derivative is 0, then your test is inconclusive and you have to go back and use the first derivative test that we talked about in part 1. So let's do an example. I'd like to look at a trig function, f of x equals sine x quantity squared, and I want to find the critical points because I'd like to study local max and local min. Remember that a critical point occurs if the derivative is 0 or the derivative does not exist. For this function, where does the derivative equal 0 on the given interval? Notice my interval is from -pi to pi. So to find where the derivative is equal to 0, that means that either sine is 0 or cosine is 0. And we're restricting our interval to be from -pi to pi. I'd like to remind you of how to use the unit circle for this interval. If you're starting at negative pi and moving in a positive direction, that means you're going counterclockwise. And so you just keep going around the circle until you get to pi. Now notice that negative pi and pi are coterminal. So what I'd like to do is, using the unit circle, I'd like to find where sine or cosine is 0. And this is what I get. Sine is equal to 0 at pi and negative pi and at 0. Cosine is equal to 0 at negative pi over 2 and positive pi over 2. The derivative is defined everywhere, so I'm not going to get any critical points from places where the derivative does not exist, because the derivative in fact does exist everywhere. But I did find some critical points, or possible critical points, when the derivative is equal to 0. I say possible because I'm not going to include the negative pi and pi because they're endpoints. So remember that a critical point has to be on the interior. So even though my derivative is equal to 0 at those points are not interior points. So I really only have 3 critical points: negative pi over 2, 0, and pi over 2. All right, so far everything I've done is similar to the first derivative test, and I'm going to show you how you use the second derivative test. Recall that if f double prime is negative at a critical point, you have a local max. If f double prime is positive, you have a local min. And if f double prime is 0, then the test is inconclusive and you have to use the first derivative test. So I need to find the second derivative. Rather than using the product rule, I'm going to use a double angle formula to rewrite my first derivative. You don't have to do this, but I just think it's a little bit easier. So I now have rewritten my first derivative, and when I take the derivative of that, I get 2 cosine 2x. And what I do is I evaluate the second derivative at each of these critical points. All right, so let's do that. My critical points are negative pi over 2, 0, and pi over 2. Testing at my first critical point, I find a max. Testing at my second critical point, I see I have a min. And testing at my third critical point, I see I have a maximum. And so I've got all my maxes and all my mins, and you can confirm this by graphing the function. I have a max at negative pi over 2, a min at 0, and a max again at pi over 2. Take care and have a great day.